In this session, we will start talking about the probability theory and random variables. What will be covered here, let's take a look at the outline. We will start with a brief introduction. Then we will talk about the repeatable experiments, sample space, and events. We need to understand those concepts. And then we will be dealing with the relative frequencies and basic concepts of probability. Then we will go ahead and talk about finite sample spaces and events with equal frequencies. Then how can we determine the number of events? That's also important. And we will talk about conditional probability and bias theorem. And then we will talk about independence of events. And finally, random variables, where we cover discrete and continuous variables, and of course the concept of expected value will be covered last. So this will be the introduction about probability theory and random variables. So we have already seen that in the previous sessions, statisticians deal with the gathering and presentation of data. So now we have an idea about how to gather and summarize that data, right? By means of graphs or histograms, whatever. However, more general focus is sampling and statistical interpretation. I think we also talked about this a bit as well, right? So your sampling should be very well. We assume that our sampling is great so that we can make some interpretation on that statistical data. And sample-based decisions on population have error rates. Why? Because each sample differs from each other by chance, right? We have covered this in the previous session as well. I mean, if every measurement from any sample would be the same, then there would be no need for statistics, right? So it is interesting because each sample data differs from the previous one or something like this. And the probability deals with this uncertainty about random events. That's what we're doing here. Now, when we talk about the repeatable experiments, sample space, and events, the repeatable experiments are required to apply that probability theory. So you need to repeat and do many experiments so that you can talk about probability theory. So what is an experiment? Any behavior or operation about our observations. So, I mean, it has a much broader definition than the scientific terminology of experiment. I mean, we're not talking about laboratory experiments here only. Just a coin toss, for example, is also an experiment. We're not talking about what's in research or drug research or something, let's say, sophisticated, or anything can be an experiment in this sense. For example, rolling a dice or tossing a coin or drawing, let's say, some pills from a box full of pills, or drawing cards from a deck of cards, or consider an automatic bottle filling machine which fills the bottles with water, for example, and for 30 centiliter size, for example. Or suppose that we're talking about a 60-watt lamp, and we're curious about how long it takes until it burns out, or runtime of a computer program, for example, the process time of a computer. So anything like this would be an experiment. That's the idea. Now the thing is, they're all repeatable, and also observations vary for each different experiment. So this was the definition of experiments, but what is sample space? The sample space is the set of all possible events as a result of an experiment. We usually denote this with capital S, the sample space, like it is a set, and small letter e's are the members of that set. They're called the events. Okay, for example, throwing a six-sided die, throwing two, tossing, not throwing, it's wrong, I guess. This should be tossing, right? Tossing two coins, or drawing 5 pills from a box of 100 pills, or drawing 13 cards from a deck of 52 cards. Yes, that's also another case or another experiment. Or filling a 30 centiliter bottle by a filling machine with a tolerance of half centiliters, for example. Or time passes until a 60-watt lamp burns out, or runtime of a computer program. How can we define our sample space in this sense here? Now let's take a look at them together so that we have an idea about defining our sample spaces. So let's start with the six-sided die, right? I know that they're very simple, but we need to understand. Okay, six-sided die, for example, we start with this. We denote it with the sample space with capital S, right? So what is in that set? So these are all your events, for example. Okay, this is how we do it. Or the second one was what? Tossing two coins. Suppose that we toss one Turkish lira coin and half lira, like we toss these two coins, okay, and we denote that they can come as, okay, heads or tails. Or the other one is, for example, again, heads or tails. This is the second coin. And what would be our sample space here in this sense? They would be what? Okay, heads and tails, right? And heads, for example. Okay, then and heads and tails, for example. And tails and heads, for example. And tails, for example, right? So you make it yourself as well. These are this is your sample set. This is your what can happen in this sense. And okay, suppose that you have a box of pills, and you have 100 pills in it, okay, and you draw 5 of them, okay. You draw 5 of them from that box. Now we will see this in combination, but the thing is, you will have lots of different occurrences, events in that say samples in that sample space. You can have this many combinations in this third scenario or third experiment. And let's suppose that you have a 52 card deck, and you will draw a hand of 13, for example, 13 hand from that deck. Okay, again, you will have lots and lots of combinations that we will discuss within this chapter again. Okay, you will have this many different 13 hands drawn from a 52 deck. So what else? Okay, filling a 30 centiliter water bottle with a tolerance of a half centiliters, right? How can we write the sample space here? Just pause the video and think about it. Now it's a bit different. So since it is it's more like a continuous variable here, we write it like this. You will have y such that, and it would be between like okay, this one and this one. Oops. Right? This is what you will have. You will have a variable y such that it will be between those values. Or if you want, you can put this like this as well, but that's the idea. I mean, rough idea about the issue. And what else? For example, the 60-watt lamp, and the time passes until it burns out, right? Until it burns out. Okay, so how can we, again, it's pretty similar, right? This time you will have your t such that t is greater than or equal to 0. Why we put here 0 as well? Okay, immediately it doesn't work at all. Maybe it's directly broken, or you can also depict it like this. I mean, depends on your that's the definition of the problem. Okay, that's the idea. And how about the runtime of a computer program? Runtime of a process, for example, computer program or something. It's pretty similar to this one, right? So that's the idea about determining the sample space of an experiment. As you have seen from our examples, some experiments have limited number of elements in sample space, and we can count them, right? Or we can write them down. Some of them we can even write them down. For example, coin toss and rolling a die examples, and we could write all of them one by one. And the other ones, we knew that they're finite, but we couldn't write all of them. What were they? Like drawing this one and drawing 30. This one was okay, we know, but we couldn't write them. And this one, we knew it, but we couldn't write it. And the other ones have infinite number of elements in it, namely these ones, for example. So that's the idea. Okay, now what is an event? Event is an observation of particular elements of sample space, such that they can also be called the subsets in that sample space. That's the idea. Okay, for example, we don't care about any 5-pill subset from a box of 100 pills, but particularly how many defective pills in that group of 5 pills, for example. So this is an event. And for example, how many heads in a 2 coins toss? Again, another event. And for example, how many aces in a 13 card draw from a 52 deck? So that's also another event. So we're caring, or we're focusing on particular elements of that sample space. That's the idea. So the events are combinations of elements that we care for in that sample space. And how do we address them, or how do we define them, is like this. Let me just try to show it to you with sets. Suppose that you have event A, and we will denote it with A, for example. And when we talk about a nut, for example, or the complement, we're talking about the complement of A here. Complement of A here. Now we're talking about all other events. All other events other than A. Okay? Other than A. So it means that it is the complement of A. All others. So when we want to represent it in a, let's say, set theory or with sets or something, suppose that you have A here, and this would be your complement A. And so if you have, for example, A union B, for example, for 2 events, it would look like this. Suppose that they're you're talking about this region here. Or if you have again A and B events, but you're talking about their occurrence at the same time, for example, now we will be talking about particularly this part where both of them happening at the same time. And what if they are mutually exclusive events? Okay, mutually exclusive A and B events, for example, okay? If they are mutually exclusive, now it means that they cannot happen at the same time. If A happens, B cannot happen, and if B happens, A cannot happen. Can you think about such events? Just think about it. Pause the video and think about it, about some examples, okay? Think about at least 2 examples, for example, from the examples that we had seen so far, for example. And how can we represent in this case, your A intersection B would be equal to the empty set. Okay, now let's just try to work on an example together. For example, we're talking about time. Okay, time passes for a drug to take effect in blood. Okay, take effect in blood, for example. Okay, and let's just write the sample space here. It's pretty similar to the example we showed a few moments ago, right? Like something like this, or okay, this one is also possible, but I will stick to the textbook examples. Okay, so I will just write it like this. So that's the idea. Okay, this one is like this. So okay, now let's define some events here to play with. Okay, let's define some events here together. For example, event A, what is this? It is T such that T is less than 10. Okay, we will have event B, for example, and it will be T such that your T is greater than or equal to 5 and less than or equal to 20, for example. Okay, this would be your possibly event B. And let's define our last event as C, where you will have your T such that your T is larger than 15, for example. Now we have 3 events in that particular sample space. Okay, now let's play with them together. Okay, I will use this space efficiently. Let me just try to do it. A union B, for example. Now, what is this? Do it with, just pause the video, get your pen and paper and do it yourself as well, and pause where it is necessary. Okay, this would be something like this. And what should be A intersection B, for example, right? Okay, A union B is something like this, you see, from here. And what would be A intersection B here? Think about, it should be between them. Okay, it should be something in between. Okay, 10. Okay, something like this. And let's talk about B union C, for example. And it should be, we're talking about now B union C. Okay, as you see, it is obvious that it is larger than 5, right? Larger than or equal to 5. Okay, it would look like this. T equal to oops, I please stick to this terminology. Okay, we also forgot here to write T such that. Okay, now it looks more beautiful. Okay, just write them as beautiful as you can, so that we will stick to the terminology. And what about B intersection C? As you see, it would be T such that it would be larger than 15 but less than or equal to 20. And what about A intersection C? See, it's 10 and okay, less than 10 and more than 15. It's the empty set, right? And how about A union C, for example? It would look like this. If you have an occurrence like this, you will write it like this. T is less than 10, or your T is more than 15. You will denote cases like this. And what about others? You will have your, okay, this would be your, okay, what is your A complement here? Oh, it's T such that T is larger than or equal to 10. Since equal is not included here, we need to put it in the complement. That's the idea. And what else? Finally, the last one from the textbook, it is C complement, and it's the T less than or equal to 15. So that's the idea about let's say particular events in our set of experiments. So we can never know a event or event A will happen or not after an experiment. Okay, it's impossible to otherwise, like it would be something like magic, right? Or like a prophecy or something like this. However, we can have an expectation about the probability that it will happen or not. That's very important. And this expectation leads to a need for probability theory. So it's very beautiful. Don't forget about this. Now, let's try to solve an example from our textbook together, okay? Let's solve this 2.2 example from our textbook together, okay? What is being asked to us in this example? Let me summarize you the question here. Namely, we have let's say a place like this, or a graph like this, D, E, F, and G. Oops, can I write here? It's not very good, so I want to, like, can I take them a bit lower? Okay, I managed it. I'm learning, right? Okay, and G, H, I. Okay, now there are some connections between those, okay, letters, okay, like this. And what we're trying to do here is to write a computer program that takes us from A to I. Okay, we will travel within this graph. Okay, we're trying to go from A to I. But we do two things here. With 50% possibility, we go right, or 50% possibility, we go up if we need to make a decision. If we need to make a decision, right? So, for example, do I have to make any decision here if I'm at C? No, because the only way is, the only actions allowed are to go right or up. In C, if you are at C, for example, with 100% probability, you will go up, because there is no way to go right, for example, in this sense. But, however, if you're at E, for example, you will choose between either going this way or this way, with the possibility of 50% going in each direction. So that's the idea. with the question here, okay? And the only allowed actions are right and up. Now, what does this question asks us? Okay, so first it asks us to write down the sample space, okay? And let's write down the sample space first here together, okay? So I will write it. I mean, just pause the video and do it on your own if you like, but we will write this, okay? Like you will have, for example, let's go A, B, C, F, I. Okay, that's possible. You will also have A, B, E, F, I. Right? Does that make sense? Let's use other colors, okay? And you can have what else? A, D, E, F, I, A, D, E, H, I. Okay, and we will have what else? A, D, G, H, I. And what else? I think we forgot something, right? Where is your A, B, E, H, I? Right? That's also missing here. A, B, E, H, I. Okay. I hope we did this correctly. A, B, E, H, I. A, B, E, H, I. This is the first part of the question. And in the second part, the author asks us to determine in how many of those cases or of those events there had been 3 decision points that you need to make a decision, right? So in this, for example, let's take a look at this subset A, for example, and it would be, what should you put here? You can go ahead and directly look it up from the sample space. What are my decision points here? Let's mark them. Your A, B, no, F is not included here because you need to go up. E, D, that's it. Otherwise, they're not included. So we're talking about any combination of 3 of them in those examples, and you will have A, B, D, E. A, B, D, E. Okay, A, B, D, E. You look for them like A, B, D, E. No. And A, B, D, A, B, E. This is lovely. And A, B, D, E. Oh, lovely. A, B, D, E. And A, D, no. A, D, no. Nothing else. And A, B, E. Oh, this is lovely. Okay. So that gives us the subset of this part A, B, E, F, I, and A, D, E, F, I, and A, D, E, H, I, and finally A, B, E, H, I are in your particular subset event A, that we can write them like this. So all of these elements are within that subset. So that's the idea, and that's one of the examples that would tell us what could happen. So when we talk about the relative frequencies and probability, we're talking about the relative frequencies, the number of events over all repetition of those events. And when we take a look at the properties of the relative frequency, we can come up with something like this. So like it's the first one is that would be something between 0 and 1. This is the first thing. And the second one is like your FA equals to 1. It means that it always happens. It always happens, okay? No matter what, it will always happen. If your FA equals to 0, what does it mean? It means that it never happens, right? It never happens. And okay, the last one is if A and B are mutually exclusive. If A and B are mutually exclusive, so your FAUB should be corresponding to those both frequencies added together. This was all about the simple properties of relative frequency. So, but stability is another issue here, all right? So, stability of relative frequency depends on experiments. Suppose that you have k repeats here. An experiment is repeated k times here. Like you will have like k1, k2, k3, like up to kr. You will have like all experiments, okay? Total experiments here. Total experiments here. Total experiments. And you will have a particular occurrence here. You will denote it with A, for example. And it would be your total, again, oops, I'm sorry. It would be your total A occurrences. This is what you're dealing with. And your relative frequency here would be something like this. These are happening. You see them over and R. So here, if you increase R, your relative frequency becomes more stable. If you hypothetically go to infinity here, you will have infinite number of experiments here. You will have like the ideal or more expected outcome. For example, suppose that you're tossing a coin and you will just denote having a tails with you will counting the number of tails here, and you will have one value here, for example, and 0 corresponding to heads, for example, okay? So what is the frequency of tails here? If you're curious about this, and suppose that you toss it once and you get what? You toss it for once, and this is your experiment number, this one, and this is the what you have as let's say tails, and suppose that you're denoting them with 1, right? And you're counting them here, so that's the idea. And it means that you will have here, for example, heads, and in the first trial, okay, it's 1. In the second trial, oh, you get a tail and it's 1. So in the third trial, you get another tail. Now it adds up to 2. So, but what is the probability here of getting that tails? In the first experiment, the probability was relative frequency. I'm sorry, not probability. The relative frequency was on this one. Relative frequency can be seen like this. It was 0. But here, from 2 tosses, you get 1. So it corresponds to your relative frequencies 0.5. this one 0.62, and you get another one. So it's just this, as you see, it is just oscillating. But if you increase the number of experiments here, it will eventually become more stable as you go ahead. And it looks like this here. The number of trials here, what you have, your experiments, and their relative frequencies are given here. You see, they just start with a, let's say, oscillation here, but as you increase the trials, they will eventually become more stable. Suppose that you continue that experiment or those trials up to infinity. Now you will get your let's say perfect outcome or expected probability here. So now that's the idea about this. So when you take a look at the properties, the thing is, when you focus on those relative frequencies going to infinity, now this is called the probability. The probability of an event is when your trials go to infinity. It will settle to a value, right? It will settle to a value. And now let's take a look at the properties of probability to get. Okay, let me try to write them down. What were we talking about? The properties of the probability, right? So it is your probability of A, event A is the limit of your n when your n goes to infinity, and A over your sample space. Okay, so the thing is, when we write down the probabilities here, for example, here you will have your sample space. Okay, S corresponds to sample space. And your A is corresponding to that particular event, and we're talking about the probability of A here. Like we're talking about the properties of PA here, and it would be something between 0 and 1, and the probability of your sample set is 1 because it's your sample set. Okay, and if A and B are two separate events and they're mutually exclusive, then probability of A union B, like their probabilities can be added together. So that makes sense. If you generalize this, if all of your events, if all AI events are mutually exclusive, then what happens? You can write it in a more general way, right? Probability of union of from I to like infinity events here. We'll have lots and lots of events, right, until infinity. So it would be probability of A1 plus probability of A2 plus going up to probability of AK. Okay, not surprisingly, if all of them are mutually exclusive, you can add them up. Now these were some properties about PA. Now let's take a look at some rules for PA. Okay, more rules for PA here, like for example, probability of the empty set is what? 0. Okay, and the probability of A equals 1 minus probability of A naught. Okay, that's the idea. And now if you take this here, like probability of A naught plus probability A would give you what, 1, so it means that this is your probability of sample space, right? But that's the idea. So okay, great. And what else? Now, if they're not mutually exclusive, probability of A union B, so probability of A plus probability of B minus probability of B intersection C, right? Pause the video and think about it. I hope you see this, because if they are not mutually exclusive, then it means that they can correspond. They have some common parts here, namely this part, this one, right? So, I mean, if you add this and this here, it means that you added this space twice, right? So you need to subtract that part here once. That's the idea. So good. And if you want to, for example, write down probability of A union B union C, what should we write? And what should be our structure here? Or here, A, B, C. Pause the video and do it on your own. We should add them up, right? We should add them up, not surprisingly, add them up. And it should be probability of A plus probability of B plus probability of C. All right, it looks pretty similar, but since we just added these parts multiple times, okay, twice, we need to subtract them once, okay. Probability of A intersection B minus probability of A intersection C minus probability of B intersection C. So that would be your answer. Is that right? Anything missing here? Okay, think about it. Okay, just be careful. We subtracted this part like multiple times this time, so it means that we need to add it in the end to make it more correct. But that's just just making life easier for us to understand it here, but that's the rough idea, and you can go ahead and think about it and try it on your own as well. Okay, the thing is, I suggest you to read the which page? It's the 70 I'm sorry, 67th page of your textbook. Read it truly, okay? 67th page of your textbook, read it truly, and then please watch the next video carefully to have an idea about deciding about how many, to answer this question, trials you need to decide on the probability or outcome of a coin toss, for example. Okay, like I mean, or whether that coin is I mean a healthy coin or unbiased coin or not. For example, suppose that you toss it 10 times and you get 9 tails and 1 heads. What does this mean? Or you will have 1 tails and 9 heads, for example. 1 tails and 9 heads, for example. What should it tell us? Please watch that video as well.